So with this talk, I want to give you actually a panoramic view of my current interests. It starts with problems, the so-called free discontinuity problems that go back to the Georgi and all his school. And I'm going to actually merge them with another theme, which is also very popular among some of us, which is the study of multi-scale problems, more precisely homogenization. And so we're going to talk about models that essentially translate into the situations where you have a phase transition that is followed, or actually goes in tandem with a high oscillation phenomenon. And then we're going to pause, and I'm going to say, well, hey, by the way, a lot of what I said has actually translation, not quite, but almost, to a completely different context, which is the context of basically training schemes and machine learning schemes for image processing. And so you say, well, okay, these are very different topics, so what do they have in common? Well, they have in common, from my perspective, I'm going to study them from the variational point of view, also encompass an interesting phenomenon that models, you have energies of very different dimensionality. In what I will talk about, it will basically be dimension n and n minus 1. So if you talk about materials, of course, you're going to work in R3 and going down to surfaces, which will be, of course, dimension 2, while in the context of imaging, and I'm not going to talk about videos, I'm going to talk about basically 2D cartoons, and you have 1D contours, right? So that will be 2D, 1D. Although, of course, you can extrapolate that to n minus 1, but in my mind, that's what I'm going to talk about. And again, as a common denominator is the fact that you have to actually push the boundaries of what we know in terms of spaces and that, of course, takes you into how you marry PDEs, variations, and the geometric measure theory. Okay, so let me give you a brief outline of what I'm going to talk about, which is for 45 minutes, but by the way, I started a little late, so... Okay, let's talk about materials. And so, going back to what I said, free discontinuity problems, I would say that probably the most well-known model is Hilliard. So that's what I'm going to talk about, Hilliard for phase transitions. And there, as I said, we have a transition from but at the same time, you're going to have lots of different grades of different materials that want to come together and homogenize your outcome material. And so you're going to have two. One is a parameter that tells you how fast, if you wish, you go into the transition, while the other one is how fast. But again, at this time, I don't have time. Eventually, I'll put time an evolution process in the end, but not at this. In the beginning, it's quasi-static. And so, called delta will be, let's see if I can maybe point here. Right, so you have an epsilon and delta, and delta will be how these oscillations operate. So we have two parameters, so normally you say, oh, okay, so I'm going to have three machines, right? And that was work with some of my former trainees. Then case where delta is much smaller than epsilon, which is, if you wish, first you have homogenization, then you have a phase transition. That's more recent work, actually being just submitted. with my former trainees, Riccardo Cristoferi and Likhit Ganedi. And then still with the same, we then look at the third regime, which is where epsilon is much smaller than delta, namely that the phase transition occurs first. So first you have like a surface, but then you still have oscillations occurring on the surface. This last case is it's more complicated case. The three regimes, the answers, I didn't tell you yet what the problem is, but okay, there will be a problem with the answers. And the answers would basically all be similar, but the methods. I'll wrap up that with some open questions, and then we'll change gears, and we'll go to training schemes, multi-level training schemes for denoising. Okay, so let me start from the beginning. For most of you, this is very well known. Just to set up the context, you imagine you have a fluid that likes to live in two phases, and so the energy density tells you that if you are at the bottom of the wells, and of course I think that in my mind nature likes to minimize energy, so if you are at the bottom of the well, either on one, this would be a case of fluids, one fluid, say at the well -1, the other one is at the well 1. Of course, you have an energy bearing, the spinal region, and so so a mag is your container, could be in our hand, and U is against the fluid. I'm going to talk. It's basically a question of optimal design. So in this container, if I'm told that I need to use M of one fluid, which is basically what's this volume fraction there, how can I combine them in my container so that I minimize total energy? Okay, by the way, W does not have to be my in the previous slide, which is down here, 1 minus the square square. This could actually be vector valued. It could even have finitely many wells and so on. But just keep this in mind. So you want to minimize energy subject to constant mass, and if I just do that, of course you have infinitely many solutions, because anything that looks like this type of characteristic function, which is A on a set, B on the complement, provided that the mass constraint is satisfied, we have energy zero, you cannot do that, right? So then this goes back to current here, and you say, well, yeah, okay, but how of tiny inside the matrix B, or the other way around, you could have stripes, you could have all kinds of textures. So, so how are we going to select among all these solutions? And then it was, oh, okay, let's add surface energy. Surface energy is in here. Surface energy is the dimensional integral. Why? Because if you are always on A, it's 0, if you're always on B, 0, you only see the transition when you go across, and then of course gradient pops up, right? So, and that's typical singular perturbation, probably put a small epsilon in front. Epsilon is going to be back of the envelope calculation. Epsilon is just the width of the transition length. So you go from A to B across a transition of with epsilon, and with that we have an energy that balances up. Okay, so so this goes back to my former colleague Mark Curtin, who said minimizers for this new energy, which I call I epsilon, in some sense they converge to one of the original ones, and it has two phases, but it's particularly special, especially in that inside a container it minimizes surface energy. So this goes back to minimal surfaces, right? So that's exactly what I wrote there, that you minimize the perimeter among all other configurations that satisfy the mass constraint. So this was rigorously validated by Modic and Mortala in the mid-70s using the notion of gamma convergence, which is a notion that it's used for rigorously justifying a limit of energies, not of functions but of energies, so of functionals. So you have a family of functions f epsilon, which in my case is going to be scaled by epsilon, otherwise you see nothing. So for epsilon goes to 0. So if you scale by epsilon, this is going to be of order 1. And I said that the gamma converges to limiting f if the, well, actually, I'm going to tell that in a moment, but the bottom line, and that's going to be a theorem, is that the limiting f indeed is up to a constant, is perimeter. And the good news about gamma convergence is that, well, first of all, the fact that I divide by epsilon, I don't mess up minimizers. Minimizers are the same, right? Let me first tell you what is the gamma limit, and then we'll talk about why is this important. So it's going to be a constant times indeed the perimeter. So it's the surface area of one face inside the container, which is the same as the perimeter area of the other face inside the container, of course. Because I'm working with this prototype specific, it's specified as it is here. But before moving on, I should tell you or remind you what is gamma convergence again. You have a family of functionals f epsilon. When do I say they converge to functional f? Well, when two properties occur. The first one is that every time that you have a family of epsilon going to u, the limiting energy is below the limiting of the energies, and you cannot compare in that. And I can approximate it by what we call a recovery sequence that actually matches the limits, so you don't have a gap. And a very important property of gamma convergence is that minimizers of the approximating sequence of the limit. So in this case, I will then know what are the preferred minimizers because I know now what is the gamma limit, so I know that if I start with a they go to minimize of that on my case, which is essentially perimeter up to a constant. And essentially it's because it's isotropic, so it does not depend on the direction of the normal to the interface, so you pull out the interfacial energy as a constant. But it could be an isotropic, it could be an integral over the interface of a function depending on the normal. Okay, so anyway, so that was the theorem I just showed to you. It is proved by many, many people, and this list is by no means exhaustive, and with many flavors, with multiple wells. In the vector valued case, it could even be like coupled, like in here, right? It could even be with Sergio, who is here, Conti and Vaglioni. We even did that for the case where we now have one more gradient everywhere, so that would be a phase transition not for fluids, but between two elastic materials, and so on. But the list goes on, of course.
Excuse me.
Yes?
Can you come back to gamma convergence?
Yep.
And just say a few words.
Okay, gamma convergence on the topology that you're using, okay? Tau is a topology. So, depending on topology, your limit may be different. So, you have convergence of functions here. So that's the conversion with respect to tau. In what I'm going to do, most of the time to be L1 strong. That you have some conversion L1 strong. What is the tau? The tau depends on is the compactness that you have in your problem. So if you know that energy minimizing sequences are compact in space X with the topology tau, that's the topology you adopt. It's that tau. Okay? It's basically related to. Let me go back. Tell me where. U is C1, it's H1, it's C1. The point is that the time space usually is not as nice as when you started here. Here, of course, is very smooth because I have a gradient. I'm going to end up with BV, bounded variation, because I'm going to end up with functions that only have two, and why? Because look at what I'm going to do. I'm going to I'm going to scale by epsilon. So this term here to be bounded of epsilon in front, which means that in the end you need to be at the bottoms of the wells of W. So if you only have two wells, you're going to have discontinuities, cannot be H1. Okay? So you start with a space that it's much more, that it's more regular than the time. Okay? Very well. Okay, but what has interested us also in this context is that there are now models where heterogeneities of both phases actually make the problem much more challenging and physically important. So, as I wrote here, there are situations where actually the wells are not constant, they actually depend on where you are on your sample. So if I'm here, I have an A of X and a B of X, and I'm here, I have a... and they may not be the same. And one of the papers that inspired us was this one in Science, where actually there were biologists, they were studying membrane models, cell membrane models, which were basically, when you translate into our language, was a Muffer-Chan, was a Canhillian kind of model, as I showed you before. But what they had was actually that they had this homogenization occurring in each phase, and what they observed was that, actually, they did not call it gamma limit, but they said in the limit, energy will not be a surface energy, as I showed you before, but it's actually bulk. You have to go one level up, and I'll tell you what I mean by that, to actually see phase separation. So I'll come back to that in a moment, but you look at their paper, and again, this is the typical kind that you would have for an homogenization process, right? You start with all these phases, and then you have smaller and smaller grids, if you faster and faster oscillation. In the end, you see an homogenized material, and the question is, what are the properties of this material that can be deduced from the composites that I started with, right? Okay, so very good. So that takes us to where again looks like Canhillian. Oh, but now you see I have a fast oscillation here. The potential may vary on position, and not only that, and that's what's oscillating. And you see the wells now can depend on where I am on my sample. They're not necessarily all the same. I'm going to assume that I have periodicity here, and right now it's all deterministic. I'll wrap up with stochastic in the end, but at this point it's deterministic. And so you have these two parameters. You have an epsilon and a delta, they are both going to 0. And so again, when I give you these energies, which again are for U smooth, T infinity if you wish, if I let epsilon go to 0, what do I get in the end? What is the limiting, the gamma limit of this energy, which is the effective energy carried by the photons? Okay, so let me first start with the critical case, where W and epsilon break tandem, and so here we prove that the gamma limit is, well, okay, it's still an integral over this, but now it's not, it has a surface energy that depends on the normal mu. There is a formula for, there's a cell for what sigma looks like. For those of you who work in homogenization, it's not surprising, but of course to get there you have to work a little bit. What is surprising though, is that what you get, the sigma, you can prove that unless, the problem is very trivial, sigma is really anisotropic. It really depends on the normal. Why is it surprising? Because as far as I know, in most of these models where you start with a surface energy normalization, that's isotropic, that's the initial integral, you end up with an isotropic gamma limit, not this case. And the reason, and I'll come back to that, is this relation between oscillations and concentrations. Right, concentration is the phase, is coming to an interface, oscillations come from the homogenization. Okay, so I should just very briefly tell you what sigma looks like. So basically what you do is this, oops, go back. You take a cube, say, if I give you normal nu, you take a cube that has two faces oriented with the normal nu, and then you're going to take larger and larger copies of this cube, so t goes to infinity. This goes back to Stefan Müller. And you know it's like an area, so you take the area of the interface, you divide by t to the n minus 1, and you infimize this among all possible u's that basically look like be on top and then on the bottom. You have to modify a little bit because it's not admissible, but that's basically what it is. So you modify it there. Okay. Why anisotropy? Because if sigma has the good taste of being oriented according to one of the orthonormal energy value is periodic, then if you take a point, if you take a point of that interface with normal nu, you basically just flatten the boundary, zoom in, flatten the boundary, and then you take copies of this cube and you just tile and they add up. While if it's skewed, that does not work, and so that's where the source of anisotropy is. Just okay, very hand-waving argument. The roadmap is standard in that first you prove compactness and you prove that you have compactness in BV. That's why your topology tau is going to be L1 strong. And then for gamma limit, you have to prove two properties, right? One is the gamma limitif and the other one is recovery sequence. Usually, you is where you land, because once you know that, final recovery sequence is basically it's basically an inverse problem. You know how to do that. In this case, it's actually the other way around. The difficulty was in recovery sequence. Okay, I don't want to spend a lot of time here, so I'm going to move fast and then go to the supercritical case. So again, not proof soup, but I'll be happy to tell you, give you references. This has been submitted. So this is the case where delta goes to zero faster. So you have oscillations occurring first, and then you have going from 3D to 2D, the phase transition. Here you're going to get what you expect. By the way, until our work in the literature, you needed to, there was a gap. Delta had to be much smaller than epsilon to the 3/2, but now that gap has been resolved and all you need is delta of epsilon 0. Same energy as before. You take the homogenized W, which is basically a convex application. The conditions that you impose on that are very smooth. Basically, it's going to be locally bound, nothing very sophisticated, but the results are actually work for any dimension, for multiple wells, and so on. So it's very robust, and you obtain what you expect, which is, oh, if delta goes to 0 faster, so maybe first I have an homogenization. So instead of W with a fast oscillation, what I have is a Cahn-Hilliard with this double warm. Okay, very good. So yeah. So you go back, replace that double oscillating by the double warm that now has no oscillating variable. You go back to my first, second, or third slide, and you get what you expect, which is okay. I'm not going to the strategy, but it's using the so-called unfolding theory, and we just unfold in one of the terms. The W term and not on the divisional integral. And I mentioned that because the other case, the last regime, we actually unfold on both. The unfolding technique, which goes back to credit when credit is due, goes to, well, of course, to step converged by Aller and Lutzen. And unfolding operator, I don't expect you to read, but just read the names. Heterogeneous, Denoising, and independent visiting. It's a technique where transform this microscopic phase variable into a macroscopic one. The price to pay is that you go from one integral to double integrals, but it really is a very good tool, and well, just to it behaves well with respect to gradients, etc., etc. Okay, so finally, because I still want to have time to talk about the second part, which is shorter. Okay, but now it's much more complicated, because what you expect is that, oh, first I'm going to have a phase transition, I leave bulk to go on the surface, but I still have all these fast oscillations occurring on the surface. Okay, so again, here we have moving wells. That's the regime here. Epsilon goes to 0 faster. So, okay, and we are going to do this slowly. So first, before I scale this by epsilon, let me look at the 0th order term, which is this. And you think this should be easy, right? Because, okay, this term should disappear, etc. Well, it is not too bad, but okay, but it's a paper in armor. So, okay, you have moving wells. The behavior is quite nice, near the less quadratic as you'd expect, the expansion. And it behaves quadratically at infinity. And you prove that, so this was the Arma paper that I think was published this year, 2023. You prove that at the zero Fourier term, you just see bulk homogenization. By the way, this was the regime of those membrane lipid rafts that I showed you a while ago. Okay, but they were scaling. It was not the zero Fourier term. And the limiting U's are not going to be dV, and so the U's now look like, basically they have like two phases in there. Again, zero Fourier terms for this kind of study before, particularly by Frankfurt and Müller, but without the phase transition there. So it was just basically, and they were using, and we use different methods. Okay, so then you're going to go back to that paper, try to find out how did it. So you do back of the envelope calculation again, and you realize that you can scale, you can divide by epsilon. And when you do, you get something that looks like that in terms of growth. Epsilon over that goes to 0. So this first bracket is innocuous, and when you look at the second and third brackets, that looks again like helium, right? It looks like 1 over epsilon epsilon. So let's do that. You scale both terms, and you're going to have to come up with the notion of geodesic distance, which is which actually it degenerates between points which are in between two phases, Wi and Wj. You have this geodesic distance, and then you prove that actually what you get is the gamma limit, as they said in that paper, it's bulk. You don't see phase separation there. It's an integral of omega, that's volume, but the integrand does see phase separation. That's an integrand over the jump, so the function v now has jumps. You have a v minus and a v plus across the interface, and that's where the phase separation comes in. So you have to go one layer down. So that basically validates what they claimed. And so again, remember the drafts, that was exactly what they got. What are we doing now? Well, so back to that scaling, the initial one, which is divided by epsilon. Okay, so I showed you the zero for a term, which you divide by 1, you do nothing. Then I showed you the scale of that paper, which was delta over epsilon. And now we go one more. We go up to 1 over epsilon, which is where we are here. Completely different techniques, because again, now you end up with homogenizations on surface. So now it's PDE, it's free boundary problems, if you wish, going back to the love starting, so that's the notions of like minimizers, and many other people, dear Luciano Varga, Chandol, and his collaborators, and so on. And by the way, at the end, exactly what you expect, which is you're going to first go to epsilon, like a surface, and then you homogenize on the surface. Of course, you cannot do it like that because I don't intend, but in the end, it's exactly what you expect. Open problems, well, moving wells were only done for the last regime, so we don't know for these two regimes what happens. What about stochastic homogenization? there is now work by several people like Esposito, Marziani, and Zepieri. And then you may ask, well, okay, so now why don't you let this evolve? You're going to have a parabolic kind of gradient flow equation. Can you do that? So, as far as I know, there's only two works. One is by myself with Russell Shoxi, Jessica Lim, and Riccardo Cristoferi, and independently by Peter Morford. It was his PhD thesis with Takis Ganedi. We worked exactly on the same problem. We got exactly the same results, completely different techniques, and our papers were published on the same issue of the same journal, which was Calcar PD 2022. And of course, there's much more to do on this, but given my time limit, now I'm changing gears, as I said, and I go to variational image denoising. And the question is this, so again, the context is going to work with bulk energies that in the limit reduce to surface energies. So I'm going to give you a nice image, and the question is, can you find a variational model that will allow me to denoise the image and get so let's start with a simple model, TV, total variation, that goes back to Gudin or Shafatemi, it's called the rough model. And so you add is your noise model, it's your noise the image. Q is where the cartoon lives on the plane. Is to minimize that's called the fidelity term, the distance between you and the noise image, and then you put the regularization term. It's a derivative. Why? Because you don't want to jump too often from one grade level to another grade level. So you penalize, that's T, it's just the total variation, that's what it is. Okay? With an alpha there, which is the tuning parameter. Of course, depending if you have alpha is very large, you have over smoothing. Otherwise, you have an inhibition of the noise one. So you want to minimize, right? But then you may ask, oh, okay, so here it's a simple cartoon where you start with a clean image, then I mess so I put some noise on it, and then this is the result using TV. Pretty good. Yeah, there's actually a phenomenon called staircasing. That's spurious jumps that are generated there. One way of removing that is by also including higher order derivatives. I'll come back to that. Okay, but then the question is, look, as I just said, you get different answers depending on what alpha is. So how do I know what is the good alpha? And until recently it was basically done case by case, which if you're doing MRIs, it's not optimal. So then what we're going to do is we are going to have a huge set of training data where I know what image U sub C, I deliberately mess it up with a Gaussian or whatever, I call it U sub beta, and in the end, I want to recover U sub C, right? So you do this in two levels. That's why it's called a multi-level training scheme, and eventually I'm going to have 3 levels, I think, in this talk. I don't know. We'll see. So basically, give me an alpha, and I'm going to take the TV with that alpha, and I minimize, I get the unit on alpha, and then I'm going to say, okay, now among all alphas, which one gives me the smaller cost? Which one is closer to the clean image, right? There's nothing magic about power 2. It could be any other power, but anyway. But in the imaging literature, usually people use like the L2 squared one. Okay, and so you're going to find what is the alpha bar, right? For that training data. Okay, again, you could involve higher order. That takes you to TGV, total generalized variation. And here, basically what you do is this term here involves the symmetrized gradient of U. There's a funny one. We have 2 parameters. It's better. The cost is actually smaller, but okay. You could also have parameters. Okay, so you could also say, where I know that up there it's blue sky, spend a lot of data there, and they have a very fine grid there. I don't need a very fine grid here, but right here, I would like to have more detail on what happens right in the front of the screen, so maybe I need to have an adapted grid for that, which means that you should, in particular, doesn't mean, but one way of doing that is to take a total variation that will depend on a weight, and indeed we do that, and so you can think of taking your square Q, divided it into smaller squares Li that could have different sizes. So they are just translations and dilations of Q. So they are in squares, and then you put a different weight there, right? So here you're going to have 3 levels, right? Because the first one is you start with one of these small squares. Have this picture in mind, right? I have here the big square, then I divide into squares, and then all smaller squares. So this would be 1L, okay? Not calligraphical. So you take that L, and then you're going to again find a minimizer for U alpha, the minimizer for that in that L, right? Then you take U sub alpha. So this is basically the previous problem I showed you. But now on each L now you have a different alpha. So now the weight that I use there depends on each one, has a different weight. And then again, you minimize the cost function. And then what is the best grid, right? So then you're going to minimize over all possible grids, all possible predictions. Okay, so there is a long history of that. So here is several references. But let me just move on, because I don't want minutes. You could also put the weights, instead of putting the weight on TV, you could put the weight on the cost, right? At this level is the same, which is divided by a constant, right? So on each L, you could put the reality, but on each L, but when you take the big picture, you have different partitions with different weights, it does make a difference in terms of the cost. And I'm going to give you simulations for that. Okay, so that's again a 3-level scheme, but now for the weights being put on the fidelity and not on the gradient or on the derivative. By the way, you have an optimized grid, because it could become finer and finer. How do you know it stops? And that it's very easy to satisfy, provided, and I don't want to go through that, but what it says is that if the data is well prepared, then you do have a stopping criteria, and there's an optimal grid that you get on level 1. Okay, so I'll just talk up now with pictures. So here you have, this is just TV, global, no weights. That's the region of model. So again, left to right, we have the clean image. I messed it up, and this is what you get with TV. And here I'm putting lambda is the weight on the fidelity term. So here I'm not penalizing the total variation, I'm penalizing the weight. That's what you get. But then I'm going to start subdividing this, right? And I subdivide, and I realize where I want to, as you can see, right? And even more detail there. And then, at that point, I stop, and I say, so, if I had the weighted TV model with the weight on the fidelity, the cost is the L square between what you get in the end and the clean image, right? It's the final comparison. And you see that actually putting the weight on the derivative, it's better, it's much better. We have a much lower cost. Okay, so now I weighted TV versus weighted fidelity on both, so that's what it is. Very comparable. When I do that, I don't see a big difference. And now I go to what about higher order? That was what I call total channel variation. Basically, you add a symmetrized gradient, second order gradient, so you have like almost a Hessian there. Again, I subdivide, and here I get that it was a lot of effort to put that second. The cost did not change much, right? Between the weighted TV, just one derivative, versus two first and second derivatives. You don't see it didn't change much. And this is my last slide, so what's next? Well, we are just scratching the tip of the iceberg. There's a ton to be done here. In particular now, you can go to what's the so-called Mumford-Shaw models. There are also second order models like Blake-Zisterman models. And then you can go to color images, where everything essentially is used once. If you go to red, green, and blue channels, 3 channels in R3, life is completely different. Nothing has been done there, and so I think these are